Hi, this is Mr. DeCraene, and I wanted to go over a couple of examples we didn't get to in class today. So the first equation I want to look at is tangent of x minus 3 cosine of x equals 0. You may be thinking to yourself, wait a minute, I see a tangent of x and a cosine of x, how can I possibly do it with two different trig ratios in there? Well, one of the things you want to remember is that we can use the definition of the trig functions to help simplify this a little bit. So tangent of x we can write as sine of x divided by cosine of x minus 3 cosine of x equals 0. And now you're saying, wait a minute, DeCraene, I still got two functions and now I got something in the denominator? Well, try this. If you don't like that cosine of x in the denominator, multiply everything through by the cosine of x to clear that denominator. So cosine of x times sine of x divided by cosine of x is sine of x minus 3 cosine of x times cosine of x is 3 cosine squared of x equals 0 times cosine of x is just 0. And now it looks almost quadratic. We still got the two trig functions, but we can kind of do the business in class where we replace cosine squared of x, remembering the Pythagorean identity. Going back to our handy-dandy right triangle here, on a unit circle the radius is 1, the vertical segment is the sine of theta, and the horizontal segment is the cosine of theta. So our Pythagorean identity is cosine squared theta plus sine squared theta equals 1, or cosine squared theta equals 1 minus sine squared theta. So I can take this and replace the cosine squared x with that kind of a thing. So I'm going to end up with sine of x minus 3 times 1 minus sine squared of x equals 0. I'm going to distribute the 3 and rearrange my terms so it looks a lot more quadratic. 3 sine squared x plus sine of x minus 3 equals 0. And now I've got to factor this. Actually, I'm going to use the quadratic formula. Sine of x equals, let's see, negative 1 plus or minus square root of 1 squared minus 4ac all over 2a. So I get sine of x is equal to negative 1 plus or minus the square root of 37 over 6. And that's about as far as I'm going to go. I guess I could write this as a decimal approximation. Let's see, negative 1 plus the square root of 37, that's going to be something a little bit, oops, sorry about that. So if I do negative 1 plus the square root of 37 divided by 6, I'm going to get about 0.847. I'm going to store that on my calculator so I can play with that one later. So I store 0.847 on the calculator, and if I do negative 1 minus square root 37 divided by 6, I'm going to get about negative 1.18. I know that's not going to work since I want the sine of x to be this, and the sine can't be bigger than 1 or less than negative 1, so that's an extraneous answer. So I go back to the sine of x must be equal to 0.847, and on my unit circle I look at where is the y coordinate of an angle equal to 0.847, and I know it's going to be somewhere up near the top. So I look at two angles, that one and that one, and since 0.847 isn't one of my nice trig ratios, I'm going to need to do the inverse function. So x is equal to the inverse sine of 0.847, and here's where I use that stored value on my calculator. Inverse sine of the thing I stored, and I get 1.01, approximately 1.01. So that particular value corresponds to this angle, and if I want all the angles between 0 and 2 pi to get the other angle, I'll highlight that one in green, I need to do pi minus 1.01. which is about 2.13, and that's the angle in green. So the big important idea for this particular problem is that back over here I can rewrite tangent of x as sine of x divided by cosine of x, and then do the trig substitution with the Pythagorean theorem in order to really make it work out the way I want to. So that's using a slightly different algebraic technique than we learned in class. The other problem I wanted to do was this one. 2 sine of x cosine of x equals cotangent of x. And now you're thinking, wait a minute, there's 3 trig functions in there. Well, let's do the same kind of thing. Let's rewrite it in terms of just sines and cosines. So it's 2 sine of x cosine of x equals, now remember cotangent is the reciprocal of tangent, so that's cosine of x divided by sine of x. And I'm going to do the same thing I did last time. I'm going to get rid of that denominator by multiplying the whole equation by the sine of x. So that's going to give me 2 sine squared x cosine x equals cosine x. We still have a little bit of a problem here. Well, you know what? I see cosine x on both sides, so you may be tempted to divide out by cosine x. But every time you divide by the variable, you may be eliminating a solution. So a better system than dividing by the variable is to get everything on one side. So 2 sine squared x cosine x minus cosine of x equals 0. And now we're going to do the factoring like we did earlier in class. 2 sine squared x minus 1 quantity times cosine x equals 0. So now either cosine of x equals 0 or 2 sine squared of x minus 1 equals 0. And these actually turn out to be really nice trig ratios. If the cosine of x is equal to 0, I'm thinking about on my unit circle, then I'm either up here at the top or down here at the bottom. So x is going to be pi halves or 3 halves of pi. If 2 sine squared x minus 1 equals 0, then sine squared x equals a half, and so sine of x equals plus or minus 1 divided by square root of 2. And if you are thinking back to the unit circle and those 16 key values that we've been looking at, I want the sine of x to be there or there. That would be a positive 1 divided by root 2. I can also write this as, if I rationalize the denominator, it's root 2 divided by 2. There or there. So I'm at pi fourths, 3/4 of pi, 5/4 of pi, or 7/4 of pi. So there's really 6 answers to this particular problem. Pi halves, 3 halves pi, pi fourths, 3/4 pi, 5/4 pi, or 7/4 pi. But again, the big important idea is back at the beginning, I can rewrite cotangent as cosine divided by sine, and then clear the denominators and factor. I hope this helps eliminate some of the problems that you're working on for the homework. Enjoy!